The real world is exceptionally complicated, and so I find myself visually always trying to find order within an otherwise chaotic object. When I look at a scene, I like to see the lines and structure of the fundamental objects of a scene. So there are lots of complicated moving objects in any real-world scene, but those are somehow temporary objects which can move around and aren't the fundamental essence of what I'm looking at. I travel quite a bit to conferences as a mathematician. One way that I particularly enjoy interacting with the different fascinating cities that I see is through photography. I'm continually trying to separate out structured, symmetric components from random, chaotic background components. It's very similar in my mathematical work. I'm often dealing with very complicated theoretical mathematical objects, but I'm trying to abstract out and see the underlying structure and separate this structure in the mathematical objects from the complicating noise that isn't so important. To me, prime numbers are these really amazing, fascinating objects. They're fundamental building blocks of the whole numbers, which are the most natural and basic objects in the universe. If you think about how chemicals are built up of atoms, you can visualize primes being the individual atoms connected together to give the whole number. So for example, you can visualize 12 as a chemical with the atoms 2 times 2 times 3 connected together to make the whole number. So one problem that I've been interested in almost my entire mathematical career has been on the gaps between primes. As you look at prime numbers on the number line, they gradually become sparser and sparser and more spread out, which means that the typical size of the gap grows as you look at bigger and bigger numbers. In work with collaborators, we've shown the existence of clusters of many primes all coming very close together on the number line, and separately shown the existence of gaps which are unusually far apart. One other aspect of my work has been questions to do with Diophantine approximation, trying to understand real numbers by approximating them with fractions. For example, the famous number pi is often written as 3.14, which is 314 over 100, or you can approximate it as, say, 22 over 7. And it turns out that fraction is actually closer to pi, and so in some ways is a more efficient approximation. These efficient approximations encode a lot of mathematical content about the original numbers that you are studying. A major focus of my research is developing new mathematical tools for trying to understand prime numbers. They remain very mysterious and poorly understood, despite mathematicians intensively studying them for thousands of years. To even have a hope of trying to understand them seems to require this very deep and powerful mathematical insight, and tantalizingly, it always feels slightly out of reach of current techniques. I've been with my partner Ellie for a bit over 10 years now. She's a doctor who works in the hospital in Oxford. Ellie might talk about things to do with medicine and the hospital and talk about, I don't know, like the complications of a particular medication. And I really want to know what sort of numbers we're talking about. So she might say, oh, this is a pretty rare number, but I find it super useful to just have some, it's definitely more than this and it's definitely less than this. Ellie and I are expecting our first baby. I'm naturally someone who likes to really understand things and plan things and make sure I'm in control of things as much as possible. Having a child is certainly going to force me to embrace a certain amount of uncertainty. I'm super excited about having a kid. I guess I would be hopeful that I can happily merge together my current fairly mathematical life with the new family life that will be a very important part of me in 6 months' time. Other mathematicians who've become fathers have told me that they've been able to do it, so I hope I can do it too.